A good friend of mine and also my housemate. And unfortunately, I'm still going to probably butcher her last name, which is a little embarrassing. But I'm happy to introduce Danuta Wisniewska. And she will be talking to us today about the scaling of foraging behavior in cetaceans. Dania actually started off as an oceanographer. She obtained a degree in oceanography from the University of Gdańsk in Poland. As an undergraduate, she took some courses in the Arctic in Svalbard, and that's when she actually realized marine mammals are the best. So she decided to, or she ended up joining the lab at Aarhus University, the Marine Bioacoustics Lab, where she studied the sensory ecology of echolocating whales. After graduating in 2013, she continued to collaborate with that lab, and that's actually when I met her, when I was working in Denmark as a postdoc. But she officially joined a different lab where she was studying the foraging ecology and the impacts of anthropogenic noise on harbor porpoises, and I think you guys will hear a little bit of her data about that research today. Last year, she moved to California to join the Goldbogen Lab at Hopkins, and she's starting to work with larger animals, so she's applying some of the tools that she developed with harbor porpoises to study the foraging ecology of some of the larger cetaceans. So that's what she'll be talking to us today. And then, unfortunately for me, I'm losing my housemate this May because she has received a Marie Curie postdoctoral fellowship. So she'll actually be moving to France in May, and she'll be moving to smaller animals where she'll be studying the foraging ecology of Adelie penguins. So with that, I'd like to introduce Dania.
Thank you, Gita, and good job on my name. And thank you for inviting me to speak here today. As Gita has mentioned, over the past 8-9 years, I have been devoting most of my time to studying toothed whale echolocation and foraging ecology. And I was focusing on some of the smallest cetaceans, mostly harbor porpoises. And last year, I moved to Hopkins to study blue whales and their foraging. So that's why I decided to focus my talk on body size and the effects of scaling on the foraging of cetaceans. And because throughout my career, some of my tools have been multi-sensor tags, I decided to start off by talking about how we can use such devices to study foraging in cetaceans, both in baleen whales and in toothed whales. But I know that one of my lab mates, Dave Cade, gave a seminar here a couple of weeks ago, and he covered a lot of the baleen whale work. So I'll try to go through it very briefly, and my talk will be heavy on the smaller guys. I'll finally talk about a scaling project I'm working on in the Goldbogen Lab at the moment, and we'll guide you. We'll walk you through some of the preliminary results of those. So let's get started. The importance of body size cannot be emphasized enough. The influence of scaling is omnipresent in an animal's life history. And its impact determines a diverse range of processes from organism performance to foraging to ecological niches. But most importantly, it drives, it's a primary driver and allometric constraint of metabolism, such that when animals get bigger, their metabolism becomes more efficient. So a larger size confers a lot of advantages to animals, including decreased lower cost of transport and the ability to fast for extended periods of time, and that in turn enhances the migratory capacities of animals. For a diving animal, getting bigger also means that they can dive for longer and deeper, because with increasing oxygen, their oxygen stores will increase and their relative metabolism will decrease. The largest animals of both past and present have been vertebrate filter feeders in marine ecosystems. Filter feeding in vertebrates is characterized by engulfment of prey-laden water and subsequent filtration of a large number of small prey suspended in fluids. This is in contrast to particulate feeding, where prey is targeted and captured individually. And these two strategies have very different energy consequences because of the very different prey intake rates and mechanical costs of feeding. Despite the prevalence of filter feedings in the large animals, there were some particulate feeders that evolved very large sizes as well. And the most famous one is, of course, is palm oil. But the evolution, the mechanisms driving the evolution of gigantism and of foraging capacity of whales is still relatively poorly understood. In odontocetes, it is hypothesized that they evolved large sizes as a consequence of echolocation, allowing them to achieve deeper and deeper depths, so to invade a greater and greater depths in the oceans, which in turn required larger body sizes and enhanced diving capacities. And that resulted in a gradual increase in body size, that, as you can see in the blue trace over there. But the mysticete pattern is very different, and it seems that the large size evolved much more recently and much more rapidly. Interestingly, it did not evolve. It evolved way after they evolved filter feeding. So the current understanding is that baleen whales evolved gigantism as a consequence of changes in the oceans that provided high-quality prey patches, which enhanced the foraging efficiency with large body size and could support such large body sizes. As a result, we now live in the world of giants, and that provides a unique opportunity to study the physiological ecology of the enormous body sizes. It is generally assumed that on average, larger sizes of baleen whales compared to toothed whales reflect the higher energetic efficiency of foraging, of filter feeding, compared to hunting single prey. However, this assumption has never been tested. It remains, the effects of body size and the foraging modes on foraging in cetaceans is also poorly understood. But let me go back to the basics and explain how these giants are feeding. So within mysticetes, there are several lineages, each with a different type of filter feeding. So bowheads and right whales are big and bulky, and their foraging apparatus consists of a muscular tongue and large and curved baleen plates. So when these animals move through the water and to feed, they go at slow and steady speeds with their mouth agape, and the muscular tongue pushes the water to the sides of the mouth and through the baleen plates, and thereby filtering very small prey. Gray whales are intermediate in size, and they have a smaller tongue, which is, however, highly movable, and it can be depressed to create suction, and thereby help in suction feeding at the benthos, suction feeding of crustaceans. And finally, rorquals are large and well-streamlined animals that have reduced tongue. And when these animals feed, they lower their jaws to engulf large volumes of prey. It is thought that their tongue can be depressed, and so it forms like a pouch that helps with to control the inflowing water. The other adaptations involve a larger skull and mandibular joints that allow for those extreme gapes and for rotation of their mandibles when the mouth is opening and closing. And finally, of course, the vestibular groove, the groove blubber, which of course lines the oropharyngeal cavity. So during lunch, prey approaches and is followed by mouth opening. And then dynamic pressure builds up, as you will see in a moment, and that propagates through the ventral groove blubber. So I'm not sure how good you can see it, actually. So now it's upside down, and it's just a wave going through the animal. As the mouth closes around the prey water, the expanded ventral pouch contracts to force water past the baleen and out of the mouth. Such direct observations, especially when coupled with morphological data, can provide incredible insights into the biomechanics of filter feeding, as well as engulfing capacities and allometric scaling of those. However, they are only limited to the animal's behavior at the surface. And so, as Alf and Dave a couple of weeks ago, the advent of tag technology has greatly increased our abilities to study these animals in their natural environment. And this is shown in a video of tag deployment by Dave, actually, I think. So these multi-sensor tags can provide us data on a lot of details on the foraging behavior, on diving behavior of the animals. So in yellow, you have a dive profile of a fin whale that is interrupted to show greater detail of the bottom face. In white, you have swimming strokes, and then in the blue, you have the estimated speed of the animals. Brocal dives are characterized by several lunge feedings. You can see that there are several lunge feedings that each is marked by a bout of swimming strokes and rapid distillation of the animal's body. Such tag data, such data can be actually interpreted and visualized to show us the animal's behavior at depth. It can also be combined with concurrent prey mapping to inform us about the animal's foraging decisions and energy efficiency. Furthermore, it can be coupled with hydrodynamic modeling that can elucidate the mechanisms that underlie the inflation and filtration processes of lunge feeding. And finally, the relatively recent addition of cameras, of high-quality cameras, to those tags allow us to not only get an inter- and intra-species context of foraging, like here, where we tagged a pair of blue whales this summer, that the animals were paired at the surface, but we didn't really know what they were doing underwater. And you can see in the moment that they are synchronizing behavior and foraging almost simultaneously. The data can also be used to verify the hydrodynamic models, as problem Dave has talked a little bit about. Those statistical signatures of lunge feeding, in terms of changes in depth and acceleration and the speed of the animals, can be used to create to construct a lunge detector that can then allow us to quantify the foraging effort of rock holes over several hours and even days. But about toothed whales, well, watching their foraging behavior at the surface is engaging, but not as impressive as, of course, lunge feeding by blue whales. It is also less informative in terms of for toothed whales, because very few, or the vast majority of toothed whales rarely, if ever, feeds at the surface. Camera tags, maybe lower this. Camera tags are currently too large for the small, shallow divers, and for the deeper divers, they are not very useful. Here you can actually see this tag has two cameras, one facing forwards and one backwards. The one on the right is forward, so you can see that even at relatively shallow depths, you cannot really see much, and at about 50 meters, you won't be even able to see even behind the animals towards the surface. What you can, however, is hear them click, so to use a direct location. was loud. Studies in captivity have shown that, like bats, toothed whales adjust their inter-click intervals when searching for an approaching prey. So in the panel here, I plotted interclick intervals and color-coded them by amplitude. In the lower panel, you can see jerk, that is the change in acceleration. And in the video, porpoise will be capturing a dead fish. And so you can see that when the porpoise is about a body length away, it starts clicking faster and at lower levels. So you can use this. This is consistent across species, and we can use this to study the foraging performance, the foraging effort of toothed whales in the wild. While tagging large animals, large toothed whales looks very much the same as tagging baleen whales. When we work with small porpoises in Denmark, we tag animals that have been bycaught in pound nets. We work with a network of Danish fishermen that contact us as soon as they find an animal in their nets, and we are there usually within a couple of hours. For the tagging, we need to lift the animal on board the boat to take it out from the nets. We put it in a soft pad and take some basic morphometric measurements. And if the animal seems to be in good shape, we attach the tag and release it a few hundred meters from the net. We usually try to keep it down to keep the onboard time to 5 minutes, and the longest we on board is 15 minutes. We use DTAG-3 tags. Now, DTAG-4 tags are actually smaller, which are wideband tags that can sample sound at up to 500 kilohertz, which is very important for recording the very high frequency clicks of porpoises. They also have a lot of additional sensors, including pressure sensors, traction accelerometers, and magnetometers, and that also sampled fast. And the longest deployments we've had of those recordings were 40 hours, but tags can provide additional few hours of sensor data only. When we process data for foraging, it's very simple. We compute spectrograms and listen to the recordings at the same time. It sounds like this. So when we see and hear a buzz, we mark it. And that's how we can map the buzzes onto a dive profile of a porpoise and count them. From that, our data, our results so far show that porpoises in the shallow Danish waters perform a short 1 to 3 minute long foraging dives to depths of between 5 and 50 meters. And during this time, they switch between different foraging strategies, targeting prey close to the seafloor, as well as in the pelagics, where they mate up to 500 buzzes per hour. Some of our animals forage primarily in the pelagics with short periods of surface feeding, and a few of the individuals engaged in some bottom grabbing. When compiled together, data from 7 animals show similar patterns. Our porpoises started foraging between 0.2 and 4 hours after release. They then usually sustained relatively high, continuous high buzz rates, which the buzz rate of up to 24 buzzes per minute and 500 per hour, and they were higher after dusk. But they were foraging strategy dependent. There were very many very short buzzes in the pelagics, hence those very high numbers, and then fewer longer buzzes along the seafloor or at the surface. And those very large numbers of buzzes then beg the question of how successful these animals were. So to address this, we tapped into the animal's echolocation. So here you again have a foraging sequence by this time wild porpoise, which looks very much like the one in captivity. We basically use animals as echo sounders. So what we do is that through a recording like this, we run a click detector, and then we extract a piece of the recording corresponding to a given distance in terms of two-way travel time. In this case, it's 10 milliseconds around, or in front, after the click, basically. We can color code that by amplitude, and then we extract another click and we align it. So if the echoes, if whatever comes after the click echoes from prey, come closer, or the animal gets closer to the fish, you will see a pattern of decreasing distances and time delay from the first click, between the clicks. We then flip that, and we adjust the width of the bins to correspond to interclick intervals. And this way, we get, rather than number of clicks, we get time on the x-axis. And the y-axis, we have delay after the click, or to a travel time. So when animals are clicking slowly, we get poor resolution images. But when the animals are clicking fast during the buzzes, we get high resolution images. And that's, in the case of a beetle, would correspond to a camera of 250 frames per second, and even higher in porpoises. So from our sequence, we could actually construct an echogram like that. And we can link that. Right. To the animal's movement through the water column to look how it's moving through prey patches. So in this case, the animal starts diving. You can see echoes from the surface that basically reflect the dive profile of the animals, and then it starts buzzing. So those repeated, those harmonics are because what I extract is quite a long time window, and if the animal is clicking at down to 2 milliseconds of interclick interval, they will be repeated. The clicks will be repeated in the echogram. So if that was a little bit too fast and confusing, here's a short sequence of that from that buzz. So again, you can see, I'll try to do that. Surface reflections over here. These are buzzes, and these are echoes from a lot of prey, which is that this animal was in a prey patch and just went from one prey after another every 1 to 2 seconds. But it's not always that easy to be a porpoise. Here's a single buzz where the animal is trying to, over 10 to 15 seconds, is trying to repeatedly capture the same prey that is escaping. And then it manages. But some of of the buzzes were up to 45, 60 seconds long. So we use those echograms and the combination of the prey tracks and the acceleration or jerk to judge whether a given sequence was successful or not. So here, when we see that there was that the prey echoes do not emerge afterwards, and there's a large jerk signature, the prey was judged to be captured, and so that was a success. Whereas here, where we can see the prey escaping, it was not a successful capture, of course. And from that, we picked 100 echograms for each individual and showed them for 4 volunteers, and estimated the foraging success of the animals to be greater than 90% on average. So then, with such high foraging success and such high prey capture attempts rates, we're wondering how large prey were the porpoises going for. And so we noticed that when the prey was acting, we could see cycling variations in the echo traces. And those we interpret as stemming from tail bleeds by the prey. Because the porpoises are clicking so fast, we can actually capture those. Because in the end, they cannot go to 100 hertz. So what we did was to trace those, and from that we could estimate the approach speed or the relative speeds of the predator and prey. So here, the speed was, if the speed is negative, that means that the speed is negative. Then that means that the prey and the predator are getting closer. If it becomes positive, that means they are drawn apart. So most likely the prey is escaping. So here we start seeing those those variations, cycle variations, and those correspond to the speeds changing, which means which can be treated as a prey escaping. We fitted a sinusoid into the echo variations, and from that we could estimate the frequency at which the fish was beating its tail, and knowing, and there's actually literature on fish tail beat frequency at different temperatures and different sizes, and assuming that the fish were escaping at maximum speed, or moving at their maximum speed, we could estimate the size of the prey. From that, we estimated most of the prey to be below 5 centimeters and on average between 3 and 10 centimeters, so very small. But what about other toothed whales? Do we get similar details in the recordings from larger dentacetes? The answer is no. In most cases, what we can detect is echoes from the bottom, so we know not only the animal's depth, but also above the bottom. The only exception so far that I've seen are beaked whales that provide as much detail as, or plain-whales beaked whales at least, that provide as much detail as porpoises. And that gets me to the bigger picture. So I hope that I have convinced all of you that the advent of tag technologies and as well as data processing techniques have allowed us to study the foraging behavior of foraging performance of cetaceans at a great detail over the past a few years. And we feel that the next step is to try to integrate data from multiple tag studies, individual tag studies, to try to test hypotheses about form, function, physiology, and ecology of the animals. In our case, we specifically want, our goal is to better understand the energetics of foraging and how that compares between particle feeders and filter feeders. We also want to see whether foraging efficiency increases with increasing body size and in both clades and the larger difference in magnitude. So our experimental approach was to create energy budgets across scale. The first step is to compile tag data sets from a large number of baleen and toothed whales of different sizes. Our next objective is to quantify the fine-scale kinematics of cetacean movements and to analyze the biomechanics of swimming, maneuvering, and feeding, and estimate their costs using bioenergetic models. We then want to determine the energetic scope and energy budgets of cetacean foraging based on their foraging rates and the available prey data. And our ultimate goal is to calculate energy budgets for foraging cetaceans by comparing the energy assimilated from just a prey to that expended during swimming, diving, and foraging. The status right now is that it is really hard to get data. So far we have data from 4 of our coal species, mostly because there's a lot of those are in Jeremy Goldblum's lab. We still only have 4 monkeys, but they have just tagged another one, and next week they're going to the Antarctic for 2 months, so hopefully you can get a few more deployments. We don't have any balanciae, any right whales or bowheads, but data has been promised to us, so hopefully soon we can look at those as well. And then we have data from 6 species of toothed whales, but for some of them we have a single, like Cuvier's beaked whale, the Barrett's beaked whale, or even a sperm whale, we only have a single individual. Although for sperm whales, just today I received 47 tag deployments, so hopefully soon our data set will look much better. In terms of quantifying the fine-scale kinetics of cetacean movements, it's ongoing. It's in parallel with the data as we collect it, as we get more and more data. We have people working on the biological models, and we are trying to parameterize it with data mostly from porpoises in terms of toothed whales and brains beak whales, and then of course a lot of data from that's already been collected for baleen whales. Yes, and the foraging rates and prey data are being extracted and compiled. So while the project is still at its early stage, I would like to share some preliminary results with you. We compared several parameters, including dive depth, duration, the duration of foraging phase within the dive, and number of foraging attempts in terms of number of lunges, and number of buzzes per dive and per dive minute. We considered each individual well as an independent observation and calculated median and maximum values for each of those wells. And then we here are plot, box plot the distribution of those data. So I will start with vocals only. And while we had krill feeders within all 4 species, there were a few individuals there are some individuals where the prey could not be identified, or some confirmed data from a single fin whale and quite a large number of humpback whales that were feeding on fish instead. So even though this data is limited, if we focus on humpback whales, I think we can still try to get at just very briefly on the effects of prey type. This limited data set suggests that while krill and fish feeders, humpback krill and fish feeders, dive to similar depths and for similar duration, and the relative duration of the foraging phase is much shorter when the animals feed on fish, resulting in a smaller number of lunges. And this could have several explanations. So this could be due to fish targets being fish prey being harder to localize, or dispersing faster and thereby limited time with the prey. It could be because of processing time being longer, or it could be because the cost of lunge feeding on fish, but probably also payoff is larger, and that's why fewer lunges are done. And right now, these hypotheses are going to be investigated, but a lot of the tags do actually have cameras, so I think many of them can be addressed, but perhaps in a separate, dedicated study. If we now focus on krill feeders only, so the mid-blue ones, both median and maximum depth suggest very weak, not significant, but positive relationship between dive depth and body size. Similarly, while blue whales dive longer than other species, if you look at maximum dives, they have the ability to dive longer. They don't seem to do that on average. However, when it comes to the relative duration of the foraging phase, minke whales seem to stand out, although we only have 2 animals. So the sample size is very low. Nevertheless, the longer foraging phase results in significantly higher number of lunges, both in terms of median and median here and maximum values, and much higher foraging rates in terms of number of lunges per dive minute. In fact, the foraging rates do scale significantly relatively with size, both as median and here mean value and the maximum values. Since at least 3 of the 4 species overlap in depth, we can compare the number of lunges and dives of similar depths. So here I plotted the maximum and median number of dives and bins of 50 meters, consecutive bins of 50 meters for all 4 species. So in most cases, number of lunges at a given depth scales negatively with size. And this is consistent with earlier studies on bluefin and humpback whales, showing that when these species dive to similar depths and for similar time, then the number of lunges decreases with body size. And so you can see it over here. The dive duration is constant, where the number of lunges decreases with body size. This at least is part due to the engulfment capacity increasing allometrically with body size, while the filter rate remains constant, which means that the animals must spend much more time filtering their prey, and the filter time for blue whale is around 60 seconds, whereas for a minke whale it is 6 seconds. But then the question is, why don't blue whales just dive longer? They are large. Well, drag also increases with increasing body size and engulfment capacity, making lunges increasingly costly with body size, with increasing body size. And that's limiting the animal's dive duration. As a result, if you look at rorquals here in blue, rorquals rarely exceed their estimated theoretical aerobic dive limit. There's the amount of time that the animals can depend on their oxygen stores alone when diving. And these are 3 different methods of estimating theoretical aerobic dive limit. But even if you focus on the lowest estimates, they're always below, almost always below. Whereas if you look at toothed whales, in red over here, then they seem to follow the predictions of the TADL much more closely, with the exception of actually beaked whales over here. Similarly, large toothed whales tend to forage deeper, and the relatively shallow dives of over here, the relatively shallow dives of the sperm whales are, I think, because of our sample size. These were two tag deployments, but they're most likely on a single whale in a single area. And sperm whales have been reported to dive to more than 1,000 meters. So I think if we include those additional 47 animals, that will go higher. On average, both toothed whales and baleen whales spend surprising amounts of time in foraging phase, where on average large toothed whales tend to capture more prey than smaller dentacetes. However, because maximum prey capture attempts do not seem to scale with size, while duration does, then the maximum foraging rates are strongly correlated with size, negatively correlated with size. Thus, with some exceptions, toothed whales seem to follow the predictions of diving physiology, likely because of their low relative cost of prey capture, while rorqual dives are certainly shorter than their TADL, most likely because their dives are much more, their lunges are much more costly in comparison to the cost of diving. The stronger negative correlation of foraging rates with body size in toothed whales may result from the smaller toothed whales feeding at the limits of their foraging rate on relatively smaller prey. We hope that we're going to obtain more prey information and incorporate that in our energetic scope models. For our tag species, we hope to be able to address these predictions. So stay tuned. And this, of course, is a large collaborative project with a lot of people contributing both their time and tag data, and not even all are listed here yet. And the Popos project in Denmark was conducted at Aarhus University in collaboration with University of St. Andrews and University of Veterinary Medicine in Hamburg and University of Southern Denmark. And as well, a lot of people are involved in the tagging and data processing. So I'd like to acknowledge those. And I will take any questions.
So how are you going to get at foraging
you have to get, probably the higher limits is what we focuses, and then you have to get some from other big laws.
How long do your tags stay on?
That varies. We don't know how long our longest porpoise can stay because the tag only recorded for 40 hours. We usually, because some of the tags have Argos transmitters, some don't. Here we can deploy the tag and we can hear it from shore and go and recover it. In Denmark we cannot because it's very flat. So we have to fly with VHF antennas. And usually, of course we don't lose the tag, so we will wait for 5 days and we've never missed a tag this way. So it shouldn't stay longer than 4 days. On baleen whales, I think they've had deployments of 60 plus hours.
When you were describing the higher rates of clicks for the shallow dives of the porpoises versus longer prolonged clicks on the deeper dives, does that have more to do with prey response or water characteristics?
Yes, it's prey. I'm pretty sure it's prey type. So the animals, even if they hunt in the pelagics during the day, that prey will escape. Most often, I'll try to escape. And those sequences are not, those buzzes are not as long as the ones along the seafloor, but they will be longer than pelagic buzzes during the night. And it's probably because the prey can see the predator, so it's harder to capture. It might be just a different prey type. The ones that the porpoises hunt during the night rarely respond. Yes?
Related to that, are the porpoise data that you have in here just from the one region and largely foraging on a single prey type? Because their prey varies in different regions, that's why your results would be different.
They could be there. They don't forage on a single prey type, I'm pretty sure, because unless it's a prey that would switch through different water layers. Our plan now, the stomach contents data from that area are at least 10 years old, and so we don't know if our data set is biased for some reason. They're going for smaller prey, or of course, stomach contents data are also partially biased because the stomach passage time in porpoises is less than 2 hours, which means that if you capture most animals by caught are, of course, in fishing nets, which means that you will find whatever was in the fishing nets. There's actually a dedicated effort now at Aarhus University to, because the DTAC force have GPS, we can then go and sample the areas where animals were and see what's there, whether they're actually going for smaller prey selectively or whether that's all that is there. And there are also students that are going to look into stomach contents of recently by-caught animals. As for other regions, the beauty of Denmark is that they are using those traditional fisheries methods. Normally, if in other countries, normally if porpoises swim to nets, they die. Pound nets are open, which means that the animals have access to air, and they are checked regularly, which means that the animals don't spend much time in the net. So in most cases, like 90% at least of the cases when we lift the animals from the nets, there's plenty of fish there. So the animals are not, they are fine in the nets. But it's only possible in inland waters because even on the west coast, it's just the conditions are too rough for them to deploy nets like that. So our data are limited to that area. I think that they use similar techniques in Canada, but I don't think that they have. Yeah, I don't think that they try to tag those animals. No.
That's it. We can thank Danya. She'll stay with us.